originally I come from Odessa. It's a nice place on the seaside, on the seaside of the Black Sea, and it's a really good place for having conferences, workshops. But in some cases, it's not the best place to do science. And it happened that I shifted from this warm and sunny place to, as I thought, that just like really cold and unattractive place to Riga, because it was my first visit to Riga. So, but as now I see that it's not so bad as I expected. So, firstly, so this transfer happened just because of two meetings between me and Arnolds Ubelis, the ex-director of the institute. So we met in Minsk and we had a meeting dedicated to Horizon 2020. And so the next meeting was with Arnolds Ubelis, who visited our city to present Framework Program 7. And because we found common interests, so the next step was my involvement in activities of Fotonika-LV. So my topic is from the previous presentations, you can see that Fotonika-LV has a good generation of people from fundamental science. But my field is dedicated to applied science, and mostly my basis is semiconductor physics and optical applications of materials. So the research what we planned here in Latvia was dedicated to practical applications of photonic materials for sensors and biosensors. So, and the motivation was very simple, because there are a lot of production of nanomaterials. Many companies produce nanomaterials, but they don't know why they produce them. It's more than they do that, but the final application is a hot topic in this area. And we concentrated on the structures what show good photoluminescence properties, and this research field was quite multidisciplinary, because we need some expertise from chemists, physicists and biologists. So here you see our recent achievements for optical gas sensing. So we made core shell nanostructures based on organic nanofibers coated with a thin layer of photoluminescent metal oxide nanostructure. Here's the SEM image, and this is TM image. The black core is just like organic nanofiber. This one is just the zinc oxide, which shows, you can see that like grain sizes and some even atomic planes. And in our research we measured photoluminescence spectra of zinc oxide. So it was excited by UV laser, and we measured the spectrum before exposition to ethanol, and then we had a permanent flux of ethanol vapors in the chamber, and within 5 minutes we had measured the spectrum, and we found that our samples were sensitive to low concentrations of ethanol vapors. We made a few tests for repeatability, and we made a few tests in order to see if this is sensitive to other organic compounds, and we found that it's really good. So it has selectivity only to ethanol. So, and later we publish it in a peer-reviewed journal. Another important field what we raised during this period is application of photonic nanostructures for biosensing. So basically, photonic materials could be an optical transducer, could be optical transducers for biosensors. If you functionalize them with specific bioselective layers, you can see and then you can see the changes of the spectrum of this transducer when when biological molecules absorb on the surface. So for this reason we use zinc oxide nanorods, and we made some testing for detection of salmonella. And so we found that the signal, the photoluminescent signal of zinc oxide changed when we changed the concentration of salmonella, and we could build the concentration dependence of the signal versus the changes of the spectrum. Additionally, we raised one FP7 project dedicated to development of nanomaterials for agriculture application, and it's still under implementation. So the end of the project will be next year in August 2016. Within this project, we generated the conception that only the multidisciplinary research could be useful for practical applications. And within this project we have exchange visits, research activities, so we organize summer schools, workshops and public conferences. And the most important thing that we involve here different researchers from different institutions. This is also like neighboring collaboration, because we involve people from Belarus Academy of Science. Also, we have visitors from Ukraine, and people from Latvia can visit the Ukrainian and Belarusian institutes to do collaborative research. So, and since 2012, we have observed like good growth of scientific achievements, because step by step building these facilities and getting people together, so we increase the quality and the amount of publications. So as Riga was a new field for me, new area for me, so I needed an infrastructure, and so I started to build an infrastructure by myself. So I found people who were interested in my research, and at the moment we are having good collaborations with inside the University of Latvia and outside of University of Latvia, so with the University of Daugavpils. And so we also have good collaboration with Vilnius University, and this collaboration is very fruitful because they are really interested in our expertise. And during the last 2 years we submitted several collaborative proposals. We have published a lot of papers, and additionally like 3 papers are in the process to be submitted. So during my stay in Riga, Arnolds inspired me to write FP7 and Horizon 2020 proposals. So this activity is one of priorities, and I suppose that we will increase the amount of submitted proposals. Of course, we need to develop them better to improve the quality in order to achieve funding, but still the first activities will be focused for not only on research but also on writing proposals and starting new exchange activities involving PhD and postdoc students. So, thank you for attention.
Are there some questions or comments? You produce your organic with an electrospinning?
Yeah, with electrospinning.
Then you separate each row or wire, or you code it as a general structure?
It's a two-step process. Firstly, we produce a network of organic nanofibers using electrospinning, and then we use atomic layer deposition to coat it with thin layers. So we can vary the thickness of the layer, and we can choose the different composites. So at the moment we have 2 possibilities, like one composite, like for example zinc oxide, or we can do nanolaminates. It means that we have two materials, aluminum trioxide and zinc oxide, and they go like alternate layers, step by step. And it changes the properties, it changes the spectra, so it's quite a good structure for applications in these photonic devices, because it's low cost, and so it produces high signal, and the surface of these nanostructures is easy to be functionalized. So
the question is, if you measure the photoluminescence as a sensing signal at the end,
yes, yes.
why do you need nanorods and you just don't take membranes, just copper?
Because we use these nanostructures because they have high surface to volume ratio, and in this case surface is dominating in the whole structure, so it defines the properties, and if I change something on the surface, I change totally the whole properties of the structure. So that's why in this case, because this is what is required for sensors, and of course they also have just like higher signal than just normal thin films. So I can minimize the excitation source if I try to apply for final device. So I cannot use laser. I will use like LED, and in this case LED has 10 times lower excitation power than laser. In this case, it will be quite difficult to see the signal. So that's why in this case, we use these nanostructures.
So you calculate that the efficiency of the luminescence is better if you have nanorods than surface?
Yeah, we have published our papers starting with thin films. So firstly, we investigated the same thin films deposited on silicon substrates, and we found that when you deposit a thin layer on organic nanorods, you have enormously new properties. So, for example, for samples deposited on flat substrates, we observed luminescence only if the layer thickness was starting like 150 nanometers. Here we observe it even for 2.5 nanometers. And it's really good because surface is the most important thing here, and if you change something there, if you have absorption, so it will change electronic properties and it will change optical properties. In thicker films, so the bulk plays an also important role, and you cannot separate bulk and surface effects.
Okay, thank you.
Yeah, thank you.